Hello again, this is Mr. Minnick, and this is, I have an audience this time. I have some participants. This is one of my Algebra 2 classes. We're talking about 4.8 complex numbers today. Complex numbers. We're trying to finish chapter 4. It's been a long, grueling chapter, and unfortunately, it's not quite over yet. Complex numbers is the topic for today. There's so many different facets of it, but I've got bad news and good news along the way. What do you want first? The bad news? Some of the concepts are really super algebra heavy. What I mean by that is you will have to have some pretty mad algebra skills to evaluate and simplify some of these things. So if you are following Math Excel and what they tell you to do, they make it more complicated than it really is, especially for the easier ones. The good news is your calculator will evaluate a lot of this stuff for you. So before we get started with complex numbers, I want to put the number system up on the board. 1, 2, 3, and so on. Does anyone recall the name of that number system? The very first numbers that you learned when you were, yeah, thank you, good, the counting numbers, awesome. Good. So these are called the counting numbers. I'm going to be grouping these together and shrinking these down, so you want to have a lot of room in your notebook because this is going to take up a big space. There's a letter that goes with these counting numbers, and it's a funny looking N like this because these have another name. Anybody remember the other name? The naturals. Awesome. Good. Good. Okay, so that is one subset of numbers. Okay, that is a subset of numbers. Those are the counting numbers. And then I like to drink milk. I always use red for this. 0, 1, 2, and so on. What kind of numbers are these now? These aren't the integers yet. We're not there yet. If you play golf, you might know the homonym for this. There we go. This has a W in it. The whole numbers. The whole numbers. Okay. So what we're saying so far is natural numbers are a subset of whole numbers. Whole numbers are not a subset of natural numbers. A whole number might be a natural number, but the number 0 is not natural. But natural numbers are a subset of wholes. Okay. So we've basically got this big hierarchy of numbers and this relationship between them. Here's where whoever helps you with your homework says, la, 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 la. We're done. We're not going to do anything else. Just because they see the name. There's a weird letter. The letter that goes with this is a Z like that. And these letters, I'm not making these up. They really exist in advanced mathematics. Anybody remember the name for these? Should you draw that? You don't have to, but if you're in an advanced math class, you'll see that, so it might not be a bad idea to write it down. So what are these called? These are the integers. Good. Awesome. Good. So these are the integers. So again, as far as how things are related to one another, natural numbers are integers. All whole numbers are integers. Some of the integers are natural numbers, but not all of the integers are natural numbers. So we keep going with subsets and subsets and subsets and subsets and subsets. This kind of reminds me of my hairstyle back in the 90s. I actually had my girlfriend. We bleached my hair for 4 hours with that really high power. You don't want to know about my hair and what my girlfriend did. Well, anyway. So my hair kind of looked like that back for a while in the 90s. So after all that, then, and I'm not bad-mouthing your 7th grade teacher, so don't think I am. Your 7th grade teacher said, okay, let's go and buy a TI-30 from Rite Aid. Because when we do, you can handle numbers like this and you don't have to worry about them because you'll never have to do them again. Well, yes, you will. What are these called? These are called the rational numbers. Okay, so the rational numbers then, again, all these fit into a big grouping, okay? So natural numbers are rational. When we say rational, what we mean is it might be a fraction, okay? If it is, it's a terminating decimal. Or It's a repeating decimal that doesn't terminate. It's a non-terminating repeating decimal, or it's a terminating decimal, like 0.125, that's an eighth. 0.11111111111, and so on, is 1/9. Okay? So rational numbers, numbers that can be written as a fraction, are rational. Okay? And the letter Q that goes with them, it took me a long time to figure out what the heck the Q is for. It's not important, but does anyone think they have an idea what the Q is for? A number that can be written as a fraction. When you have a fraction and you want to get a decimal, what do? You divide, and the answer to division is called the quotient, hence the Q. Does that make sense? So some of these make sense and some of them don't. So totally disjoint from that, totally separate from that, there's another set of numbers, and this is where your science teacher says, okay, you need a calculator. Your math teacher says, no, don't use one. Learn the right way to simplify these, such as the square root of 2, such as pi, such as e. These ones can't be written as a fraction. These are these are what? Nice, good. These are irrational. These are irrational. And if these are a decimal, which many of them are, all of them are actually, these are non-repeating, non-terminating. These are non-repeating, non-terminating decimals. Okay? If they're a decimal, they're non-repeating and non-terminating. Pi has an approximate equivalent to 3.14. I used to know it out to 70 decimal places, but square root of 2 is 1.41 and change. E is 2.71828 and change. But you cannot write those as fractions. People try, but you can't. Okay? There's actually a really comical video about the irrationality of pi that maybe we'll watch someday. So a mathematician said, okay, we got all these numbers. Everything needs a home, so let's give these a home. Collectively, all these things together exist. They really exist. For real. I'm not kidding when I say these numbers exist. And what kind of numbers are these called? Good. These are the reals. Okay? And up to 8th, 9th, 10th grade, that's what you studied. Real numbers. It kind of looks like the side cover of a motorcycle engine. A little bit. So, group all this together and shrink it down. Mathematician said, you know what? Let's try something here. Example 1a, let's solve 6x squared equals 72. Example 1b, let's try to solve 6x squared plus 72 equals 0. Let's solve these two equations. And this is going to kind of segue. We're going to come back to that, to the picture. We're going to come back to that. But let's try to solve this equation real quick. I want to get the variable x all by itself. All by myself. I want to be all by myself anymore. So what should we do first? Divide by 6. Great start. Awesome. So we divide by 6. Now, a lot of people don't know 72 divided by 6. That's fine. Let's divide it by 2 first, and then divide by 3. 72 cut in half is 36, and 36 divided by 3 then is 12. So this is 12. So we get x squared equals 12. And then we're trying to get the variable all by itself. So what should we do now? Take the square root. Take a square root. So then we get x equals, don't forget about breaking square roots down. 12 factors into 3 and 4. So this is going to be in simplest radical form. What's that going to be? Oh, 2 rad 3. Nice. Awesome. We're in it to win it today. 2 rad 3. Anything else? Anything else? Plus or minus? Awesome. Awesome. Okay. So the cool thing about this, if we wanted to, we could have solved by graphing. And that's one of the reasons I had you bring your calculator today. If we go y equals 6x squared minus 72, which is what I'm about to do right now. I am going to solve this by graphing 6x squared minus 72. Wherever the graph goes through the x-axis, that's my answer. And the graph goes through the x-axis twice. I wonder where. Let me calculate a value. And let me calculate a 0. Choosing a good bound and another good bound. Let's see. The one place is negative 3.46. Let me take a picture of that. Negative 3.46. I just wonder what the square root, wait a minute, we said 2 rad 3, right? 2 rad 3. 2 rad 3 has a decimal equivalent of 3.46. So that's my answers, right? So this is negative 2 rad 3, and this is 2 rad 3, and that's my answers. I could have solved that by graphing. Kind of. I wouldn't have got the exact answers, but I could have solved it by graphing, right? Everybody with me? Okay, awesome. Well. I'm going to try to solve by graphing. Solve by graphing. So here I would graph y equals 6x squared plus 72. So I want to know where the graph goes through the x-axis. I graph it. I don't see a thing. Scratching my head. Maybe I should go play a game of Flappy Bird. I actually can't play Flappy Bird because I don't play games. Actually, the truth of the matter is I can't get it on my BlackBerry. So the vertex here, anybody know where the vertex is? I hope somebody does. We got a chapter 4 test coming up soon. The vertex is 0 something. 0 what? 72. Wow. So let's look at the graph. Let me change my window here. Let me take my y max. Let me take this clear up to, you know what, I'm going to go all the way up to 90 here. And I'm going to go by tens. And the solution is where the graph goes through the x-axis. Where does the graph go through the x-axis? Where does the graph go through the x-axis? It doesn't. So I guess we have a problem then, don't we? Houston, we have a problem. Let's try to solve this algebraically. 6x squared equals negative 72. 6x squared equals negative 72. So following the same idea, we divide by 6. So x squared equals negative 12. So then we take a square root, and we take a square root, and we get x equals, I wonder what we get. I wonder what my calculator says the square root of negative 12 is. Oh no. It says that it's not a real answer. So we've got somebody that knows the trick to simplify this, and we're going to see that in a minute. We're going to come back to this. For now, in ninth grade, if a ninth grade answer, we said we can't solve this. There's no answer. The graph doesn't go through the x-axis. We can't solve this. Fundamental theorem of algebra says, you know what, there's 2 answers, and we have to find them. And hopefully by the end of this lesson, we'll be able to see how to do that. Any questions, comments, concerns, short debates so far? Okay, well, let's get moving then. I like to move it. So here we go. The number I, the square root of negative 12, the number 3 minus 5i, those are all numbers. They're not real. They're not real. What do we call things that aren't real? Imaginary. Okay? We call them imaginario. They're imaginary. Well, mathematicians don't like to leave anybody out. I miss having recess. Recess was cool. When I was in high school, we used to go play basketball in the gym after lunch. Anyway, that's another story. But somebody always was on some team. Even my friend Ferb, he got to play too. So what I'm saying here is we need another subset to encompass everything. And this subset that encompasses everything isn't as complex as you might think it is. LOL. So what's the name of this subset of numbers then? They're the complex numbers. When you hear the word complex numbers, all it means is, you know what? It's the reals and the imaginaries. We're not in ninth grade anymore. Okay? So I am going to write this down. I wrote this down in the last class. When you hear about complex numbers, in other words, if you're taking a test, you're reading directions, and they mention complex numbers, integers are complex numbers. Natural numbers are complex numbers. However, when you hear about complex numbers, it is safe to assume, and I know you know what happens when you assume, but it is safe to assume you will encounter imaginary numbers. It's kind of weird because real numbers are complex. Natural numbers are complex. Just because that's the way that the whole number system fits together. But whenever you hear somebody mention complex, chances are it means, you know what, you're going to be dealing with imaginary numbers. Whether you like it or not, you're going to run into them. Okay. So whenever you hear somebody talk about complex numbers, think to yourself, there's probably going to be some imaginary stuff here. Questions? Comments? Shout-outs? Mr. Minnick would like to give a shout-out to the future Mr. Minnick. Okay, so there's this thing called the imaginary unit. It's a definition. The imaginary unit. The imaginary unit. It goes by the name I. It has an equivalent value of the square root of -1, which opens up all kinds of possibilities. I is the square root of -1. No, I am not. Yes, I is. I is the square root of -1. Some of you are taking trigonometry this year. We can say this about I. I is cyclical. What's that mean, cyclical? 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 Thank you, it repeats. Repeating. Repeating. I is cyclical when raised to powers. What we mean by that is I to the exponent 1 is equal to the square root of -1, which is just equal to I. If we were to continue this, I squared would be the square root of -1 times the square root of -1, which is the square root of -1 squared. What happens when we square a square root? They cancel out. Awesome, good. So I squared then ends up equaling -1. Now, before we get too far ahead of the game here, I'm going to start highlighting stuff. I to the exponent 1 is equal to just I. I to the exponent 2 is equal to -1. Okay. I to the exponent 3, if we think about our exponent rules and how exponent rules work, this would be the same thing as I squared times I to the first. Making substitutions, that would be -1 multiplied by I. -1 times I, that's going to simplify to just be -I. So let me highlight that. I'll use my heart this time, I suppose. No, I'm going to use something else. I'm going to use a parallelogram this time. So here's my parallelogram. I cubed is negative I. Now, I to the fourth is I squared times I squared, which is I squared squared, not to be confused with Squidward, which is negative 1, the quantity squared, which is just 1. So I'm going to use my heart to highlight that one. I to the fourth is 1. Cyclical. 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 We might come back to that. I think we'll have time at the end. I'm not sure. One thing that's going to be asked of you is to evaluate powers of I. This might be example 10. I to the 486th power. And right away, you'll be able to know what this is. You should be able to know what this is right away. And hopefully by the end of class, we'll get to that. If not, at the end of class, we'll get to that next time on Thursday. Okay? Well, let's go back for a minute and fix this one here, this example 1b. Example 1b, we're going to fix it. We're going to get it right. The square root of negative 12. I can rewrite that using a little bit of magic. It's really not magic. It's just algebra. Negative 12 can be rewritten as negative 1 times 12. Right? Everybody see that? And we had this thing that we studied in earlier on in the chapter that said we can split apart radicals. That's the square root of negative 1 times the square root of 12. Since we're solving, we know there's going to be a plus or minus. What's the square root of negative 1 equal to? The square root of negative 1 is equal to I, which means then we can make a substitution here. We have an I, right? And then the square root of 12, we broke that down. That was 2 rad 3. So I times 2 rad 3. This last part's a little weird. This last part's just kind of weird. It's not traditional to write the I out front if we have a coefficient. We're just going to switch the place of those two things. So here's my answer. X equals plus or minus 2I rad 3. That's it. That's how it works. That's how it looks. Complex numbers. Got two answers because the fundamental theorem of algebra says we're supposed to have two answers. And we do. They're just not real. I could scroll up the whole way. Well, we'll scroll up to about right there. Is that good? Okay. So in a minute, I'm going to tell a story. I'm going to change names because I don't want to give away any names and I don't want to embarrass anybody. But when I was in grade school, I struggled with division. And my grade school teacher was an Italian woman about 4'11". I had another woman who taught my math class that was like 4'7", 4'8" when I was in 9th grade. Anyway, my 6th grade teacher she had a weave, or what's that called when women wear their hair like Marge Simpson? Not a perm, but a beehive thing. With her beehive, she was about 6'5", but she was really like 4'11", and she walked with her shoulders back. And there were rumors about her that she had had a hip replacement, and she had a hip, and she had some kind of cancer. So supposedly she had an appendage made. They joked around. They said it was made out of wood. I don't know what the deal was. But anyway, I don't think I'm making fun of people here. I'm just sharing a story. It will make sense, and you'll really be able to simplify square root of negative numbers when we get to the end of this. Okay. Anyway, she had an accident when she was younger, and her one eye was damaged. I had an uncle that had the same thing happen to him, and what they do is they'll put in an artificial eye. And sometimes it'll move, but it won't quite move right. But everyone knew that she had it. So in class one day, we were dividing, something like this. It was my turn. So I put the 3 up like this, and I did the 21, and I subtracted, and I got the 2. I never understood the remainder. I always thought that the remainder was just a made-up number. Okay, I never understood where it came from. So I wrote R8. And she got really excited, and when she did, her eyes opened up real big. Well, imagine somebody's got an artificial eye in the socket that's just kind of held in there by your eye. When you get all excited, your eyes open up. It fell out onto the floor. I was so like freaked out by it. Well, when you try to simplify the square root of a negative number, you might get a little freaked out. So you know what happens when you simplify the square root of a negative number? An eye pops out. Right? You simplify the square root of a negative number, an eye pops out. It's going to happen every time. Okay? All right. So, oh, that was awful. Some of the stuff that my classmates did to that poor woman. So let's look at example 2. Example 2, simplify. Simplify each of these. Number A, we'll look at the square root of negative 4. Number B, we'll look at the square root of negative 2. Number C, we'll look at the square root of negative 20. Number D, we'll look at the square root of negative 450. That probably ought to be enough for us to get the idea here. You simplify a negative square root, an I is going to pop out. So an I is going to be in the answer in all these. You don't need to do this step by step. Once you do 2 or 3 of these, you'll see what happens. This is the square root of negative 1 times 4. So it's the square root of negative 1 times the square root of 4. Wait a minute. The square root of negative 1, what's that equal to? I. So this is I times, and what's the square root of 4? 2. So I times 2, we don't write it that way. I times 2, we write it as 2i. Now somebody out there is thinking, do I need a plus or minus? And that question came up earlier today. No, plus or minus necessary when simplifying. When you're simplifying, you don't need a plus or minus, okay? It is necessary when solving, okay? Subtle difference. Right now, we're not asked to solve an equation. We're just simplifying an expression. When you simplify, you don't need the plus or minus. When you're solving an equation, you need the plus or minus, okay? So let's try this next one. Simplifying a square root, an I pops out, right? So this is the square root of negative 1 times the square root of 2. Well, what's the square root of negative 1 equal to? I. Square root of 2, we can't simplify that anymore, and that's it. That's all we get, just I times the square root of 2. Question? So the question is about the format, yeah. With the format, if your answer is I times 3 rad 7, it should be written, you should write it as 3i rad 7, right? Yeah. Okay, so if there's a coefficient, you always write the coefficient, then the I, and then the radicand after that. Okay, good question. Good question. Will it ever just be an I with the radical? Well, yeah, in part B, we saw an I with just a radical. So sometimes there's a coefficient, sometimes there's not. A lot of it greatly depends on how the number breaks down. So this next one, 20 breaks down into 4 and 5, right? So what are we going to get for this next one then? The square root of 4 is going to come out from the radical. So that's going to be what do we got? Look at that, 2i rad 5. We're in it to win it today. 2i rad 5. Good. Notes, my goats. This last one here, 450. I asked you a while back to memorize your perfect squares. 225 is a perfect square. Anybody got this one? The square root of 225 is not 25, but it does end in 5. What do we got? Got to be real careful how we write this. There's going to be an I in it. There's going to be a rad in it. The square root of the perfect square is the coefficient. 225 square root is 15. So 15 is going to be up first, and then an I, and then what's the radicand? A 2 is the radicand. Okay? I told you there was good news in all this, right? I feel like David Letterman. He laughs like that. Good news. I am encouraging you for many of these to let your calculator do the work. Your TI 83, 84, Inspire will simplify a lot. Not all of it, but it will simplify a lot of these for you. The only problem is you have to know how to set it up, and you only ever have to do that once, and then it's good to go. Whoa, what's that weird looking Y? That's kind of odd. That's supposed to be a lot. There we go. So if you're using a TI-84, let's see. Let's go back a page for a minute. Square root of -4. The square root of -4, my TI-84 doesn't like me. What you have to do is you have to press the M to the isode, the mode button, the mode button, the mode button. And where it says real A plus BI, we're going to go to the A plus BI. So I'm going to go down here to the A plus BI. I'm going to select A plus BI. I said I'm going to select A plus BI. Now all of a sudden, I can take the square root of -4. And look what I get, 2i. Ah, cool. Now, if I take the square root of -20, it's not going to give me that answer because I do need to be able to simplify radicals, okay? 2i times the square root of 5. Well, let me just do 2 times the square root of 5. 2 times the square root of 5 is that 4.47, so the square root of -20 is the 4.47. So here's the thing. You do still need to know how to simplify radicals, but this will help you a little bit, right? Any TI Inspire users? Okay, check it out. On the Inspire, your menus might be a little bit different than mine, but let's go Home. Let's go to Settings. At this screen for Settings, you might have one that says Graphs and Geometry or General. Go into General. So we're going into Settings. I'm going into my document settings. And the one you want to change is the one that says Real or Complex. Real or Complex. We're going to change it to Rectangular. We're going to change that to rectangular. I'm going to click make that the default. It's going to say, do you really want to do this? Yes, I do. I went to Home and then Settings, and then it depends what operating system from there. Some operating systems you need to go into General, or on mine I go into Document Settings. Okay. So I made it rectangular. Once I do that, I could go back into my current document here, and I want to take the square root of -4, and it says that it's 2 times I. Everybody doing okay? Well, example 3, I guess, is what we're on now. Simplify this. Simplify this. Let's go with 3 minus I minus the group of 6 minus 4i. Okay. Now here's the funny thing. I don't know if it's funny or not. The calculator will do this for you. It will do this for you. It will give you the right answer. However, the book makes this a mountain. The book uses some weird formula that says a plus bi plus c plus di equals a plus c plus b plus d I. The book does all that. Forget all that. I'm not the book. Never have been. Never will be. Math Excel. The book. This is real easy. Combine like terms. That's all you got to do. Like terms. Well, what are like terms? 3. That's a number. It doesn't have an I next to it. What's like to the 3? The 6. So if I look at the operations here, what I've got is 3 minus 6, right? Well, what's 3 minus 6 give me? Negative 3. Everybody follow so far? And then the other terms that are like are this negative I and this term here. So that other part of this, I have negative I minus 4I, right? Because that minus 4I is in the parentheses. So that's negative I minus 4I. So what's that? How did I get the second minus? This is kind of weird. Let me get out my magic marker here. This minus is this minus, and this minus is this minus. Yeah, so that's going to end up being, this is going to turn into plus right there, right? So then what's that going to give me as far as my eyes are concerned? Plus 3i. And that's the answer. Your calculator will do this, okay? Now, where you find I on the calculator, that might be a mystery. That might be a mystery. The group of, let's see what it was. Well, it's 3 minus. I'm not going to use capital I, which is on the x squared key. I can't use that I. I got to use little I. On the TI-84, it's located on the decimal key. The decimal key. So it's not alpha, it's second decimal. So 3i, the group, minus the group of 6 minus 4, second decimal I. Okay, and there we go. So again, that can be found on the decimal key. Sorry about the loud snap there. I forgot to turn the volume down. Any questions, comments, concerns? TI Inspire users, write this down because you're not going to use the right I. You're going to use the wrong I. It's going to give you variable undefined, isn't it? How many people tried that and have got variable undefined? Because you're not using the right I. You got to use the right I. Write this down. To get the right I, let's see, we went with 3 minus I. If you use the I on the keypad, that's not the right I. Minus the group of, what did I have, a 6 minus 4i? Watch what my calculator says. It says, you know what, you're not using the right I. We're not going to do anything. There's more than one way to get to the Eastwood Mall. I take the bypass or the strip if I'm going to go to the hot dog shop and want to go through a lot of potholes too. But you don't use that I. The I that you need to use, let me see if I can take a picture of this keyboard and bring great attention to it. The I that you need to use is the right I, and it is found right there on the pi button. That's where you get I from, okay? That's where you get I from. You don't need, on the TI-84 you hit second decimal, but on the Inspire, you don't need to hit second. So let's see, we have the group of 3 minus I, so I'm going to hit the pi button. I just hit the pi button and choose my I. So 3 minus I, that group, minus the group of 6 minus 4, and then I use the pi button I. Make sure I use the right I, and there we go. How we doing so far, all right? Math Excel, I don't know why they make this as difficult as they do. Okay. Any questions, comments, concerns, short debates up to that point? Okay. Well, let's go back to the cycle of I. I's cycle. I's cycles. I to the first is I. I to the second is -1. I to the third is -I. I to the fourth is positive 1. Some people call me the space cowboy. Some people call me the gangster of love. And some people call me Maurice. Some people try to come up with their own shortcuts for this, and we're gonna set the record straight on this. Okay, let's go to I to the fifth. I to the fifth. If you think about your exponent rules, it's I to the fourth times I to the first. Does everybody follow that? Okay. I to the fourth. Let's use some substitutions. That's going to be 1. And then I to the first, we said it's just I. So 1 times I is what's 1 times I? It's I. All right. Let's keep on moving in the cycle. I to the sixth would be I to the fourth times I squared, right? Well, I to the fourth is 1, and I squared is the same. Well, I squared is negative 1. 1 times negative 1 is negative 1. Interesting. Very interesting. I to the seventh is I to the fourth times I to the third, which is 1 times negative I, which is negative I. Anybody see it yet? I to the exponent 8 is I to the fourth times I to the fourth, which is 1 times 1, which is 1. All you need to know for I and its cycles are this one, this one. Let me actually use different shapes around this. You need to know I to the first. You need to know I to the second. You need to know I to the third. And you need to know I to the fourth. If you know those 4 powers of I, and you know a thing or two about multiples, you could find any power of I. Let me highlight a couple things real quick here. Where's my highlighter? This first and this third one, those are not real. So let me say something about that. Odd powers, not real. Odd powers of I are not real. What can we say about even powers of I? Even powers of I would be like I squared, I to the fourth. Well, that's negative 1, and that's positive 1. Those are real. Those are real. Okay? Every fourth term, the cycle repeats. Everybody catch that? So here's where things get interesting. I to the 17th. If I wanted I to the 17th, what I would need to do is figure out where this belongs in the cycle. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I to the 17th falls back into the cycle the same as I to the first, right? What would I to the 17th power equal? It would equal I. We could verify that on our calculator. Get the right I to the exponent 17, and we get I. What if the number's huge, though? What if it's like I to the 399th? This is where things get interesting. Are we going to go around that cycle and count up to 399? You could just divide. Now, it's real crucial what you divide by, and this is where people get it twisted. This is where people get it twisted. It's real crucial what you divide by and what you make the pivot point. What are we going to make the pivot point here? What are we going to divide by? Somebody said it? Thank you. We're going to divide by 4. This right here, this fourth part in the sequence, that's what we're going to divide by. We're going to divide by 4. If it's a power of 4, it's there. Wait a minute. What's the closest power of 4 to 399? Isn't 400 a power of 4? Or a multiple of 4, I mean? Not a power, but a multiple. So if this were 400, if we had I to the 400th, I to the 400th, I said, I keep coming up with these little check marks. I to the 400th would be right here in the cycle, right? So I to the 399th would fall back here. So what's I to the 399th going to be? Negative I. We had a question. Why would you divide by 4? Because the pattern repeats every 4 terms. And a lot of people want to divide by 2. If you divide by 2, you know it's going to be either 1 or negative 1, but you don't know exactly where it's going to fall in the cycle. If you divide by 4 and then go backward or forward in the cycle, that'll get you there every time. If you go I to the 26th, okay? I to the 26th. I don't know exactly where that's going to be, but I know 24 is a multiple of 4, and that would be down here. So 25 then will be back up here. So I to the 26th then would equal negative 1. Okay? So it always hinges around I to the 4th power. Okay? If you don't quite get that, we'll revisit that next time. It's been real. It's been fun. Hope everybody has a great day. I'm going to leave an open mic for shout-outs. I'm walking away from the microphone for shout-outs.
Shout out to Nate Emmons.